All right, welcome to this YouTube channel again. So today we are going to be talking about the plane waves in a conducting medium, and we are going to derive the equation for the skin depth. Now, if you have ever wondered why radio waves cannot penetrate deeply into metals, or also why electrical currents in high frequency circuits flow only on the surface of conductors, then the answer to all these questions all lies in the remarkable electromagnetic phenomenon which is known as a skin effect. So to further understand the skin effect, we must first study how electromagnetic plane waves behave inside the conducting medium. Unlike waves in free space, electromagnetic waves entering a conductor lose energy continuously as they propagate. The amplitude decays exponentially due to the presence of electrical conductivity. So in this lecture, we are going to derive the wave equation for a conducting medium from Maxwell's equation. That we introduce the propagation constant and also obtain the skin depth or skin effect. So we're going to define some parameters: the conductivity, permittivity, and the permeability. And also, we are going to define the constitutive relation, which is given by these expressions. We're also going to consider Maxwell equations in phasor form. So these are Maxwell's equation in phasor form. So we'll have the Gauss law here. This is Faraday's. This is also the Gauss law, and this is the Ampere's Maxwell's law. So we are not going to be using the differential form or the integral form here. We're going to be focusing our attention on the phasor form of Maxwell's equation. So let's derive the wave equation for E, the electric field. Now, if we take the curl of both sides of equation 2, this is equation 2 here. So if we take the curl of both sides, we are going to have this expression. And now we can expand this by using a vectorial identity. The expansion of that is going to give us this expression on the left. And for a source-free region, this must give us 0. So we're going to have this expression after substituting the 0. So this is what we're going to have. Then if we do a little algebra here, first of all, this is going to be the wave equation for E in phasor form. If we do a little algebra, we are going to have this expression. You see, we have to pull out j omega out of it, and it interacts with this to form this expression here. And this is what is left inside. It is going to be called our complex permittivity. Look at it because of the complex term here. So it's going to be called our complex permittivity. And if we include that, our equation from equation 4 becomes this. So look at what we have here. Mind you, look at this is already our complex permittivity. The solution for this equation will be given as this. Don't forget, this is the pattern in which Helmholtz equation occurs. Helmholtz equation always occurs like um we have this square, let's say y plus k square y equals 0. That's Helmholtz equation. Now let's also let k squared to be equals to that coefficient. If we take the square root of both sides, we're going to have this expression here. Now, you must know that we have substituted back our complex permittivity here. So we have substituted it back here into this expression here. So we can say the entire expression here is equal to the real part minus j times the imaginary part. So look at what we are going to have from here, where we have made this expression here to be equals to a. So let's review that. Now we can expand this expression here by letting it to be equal to alpha plus j beta. So you see that everything is equal to gamma. This is called our propagation constant. Alpha is called our attenuation constant, and beta is called our phase constant. So if we solve this equation by squaring both sides, we're going to have this. And by comparison, we're going to have this and this as well. So if we solve this equation for beta, we're going to have this expression for beta. Now we can substitute beta into this equation and we end up having this. So if we rearrange, we have this again. Now I want to use the limit we gave before. So this is the limit we gave before. For a perfect conductor, this expression must be far greater than 1. And if it is far greater than 1, it means A is far greater than 1. So 1 here is not going to have any effect on this expression. So you see that we can write 1 plus this expression to still be this expression. It's just like A is infinity. So infinity plus 1 should still be infinity. So approximately alpha square should be approximated to A square over 4 alpha square. So if we solve for alpha, we're going to have this expression. Don't forget we have substituted back A here. If we substitute back A, we are going to have this expression for alpha. Then if we substitute A and alpha here, we're going to have the same expression for beta, but just with the negative sign. Now, look at our equation that we had before. This is supposed to be K, please, so change yours to K. So if we go back to this, our previous equation here, and now substitute in this expression here, we had alpha plus beta. If we substitute for alpha and for beta, we are going to have this expression. And this expression is going to now be equaling back our KR minus JKI that we had before. Now we can see from this expression by comparison, this is KR and this is KI. So they are both equal value for a perfect conductor. So let's consider our electric field, that is including this partial part and the time part. So this is going to be our electric field for Z, comma X. So if we substitute our K, don't forget K was equal to, we had K equal to KR minus JKI. So that's our expression for K before. So if we substitute it back here into this point here, we are going to have this expression. For which if we rearrange, we end up having this. So in this equation, this is the equation for our electric field propagating in the Z direction. So this is going to be the oscillating part, the part that causes the wave to move like a sinusoidal wave function. And this is the part that tells us how the amplitude of the wave decays in time. So has something to do like this. The skin depth is defined as the distance at which the amplitude falls to 1 over 8, 1 over exponent of its original value. So 1 over E times the original value, the original amplitude is equals to this, and Z becomes our skin depth, which is Z is equal to let's call it delta. So if we make this can cancel from here, this can be written as e to the power of negative 1. So if we cancel e out from here again, we're going to have this expression, because we have negative 1 is equal to negative ki times this, of which this guy is equal to this. So our delta is equal to 1 over Ki. So these are expression for the skin depth of the material. If you look at this diagram, you see that this equation, the part of our electric field here, it is this oscillating part. This is the part that shows how the amplitude decays exponentially. So if we combine this particular graph with this particular graph, we're going to end up having our electric field graph as this seen here. So the physical meaning of skin depth is that it measures how deeply an electromagnetic wave can effectively penetrate into a conducting material before its energy is significantly attenuated. So as the waving propagates, it induces currents that dissipate energy as heat. I know you know that. So causing the wave amplitude to decay exponentially. So next class, we're going to be talking about something, or we're going to be solving one or two questions on this skin depth. So see you next class.